Okay, welcome students of grade 12 studying physics bilingual program 2019-2020. I am Mr. Sayed from Al Shamoukh International School in Muscat. Today the topic we are going to study is standing waves. Standing waves. This topic is actually divided into two parts. If you look at your syllabus, 2.4 is related to standing waves in string. So we are going to study only this topic related to standing waves in a string. My lesson is divided into few parts. The first part is how standing waves are formed. So it's related to formation of standing wave. Formation of standing wave. The second part is to discuss the characteristic of standing waves. The third part is to quantitative it's a quantitative discussion. Okay, so it's a quantitative discussion of standing wave, and here we will be deriving few equations. So first let us start the formation of standing waves. Consider we have a string. Okay, now the string is attached and fixed from both ends. Now consider a traveling wave is produced from one end by any agent or any machine. So this is how the traveling waves are produced in a string, and these waves are traveling in this direction. Now, for example, this point is fixed. Okay, so this traveling wave will move in the string and will be reflected back from the fixed point as a traveling wave of almost same amplitude. So now we have two waves, one which is sent by any external agent from here, and the other wave is the one which is reflected back from the fixed end. Now students, these two waves, this one and this one, have something in common. Number one is their amplitude, A, that's same for both of these waves. Number two, the frequency, that's also same for both of these two waves. Number three, the speed of these waves is same. So both of these waves have same amplitude, same frequency, and same velocity, and they are traveling opposite to each other. Now if these two waves, they superpose with each other, they are going to form a standing wave. So after superposition, the same string will be vibrating in this fashion. So this was one fixed end, and that was other fixed end, and you will see the string will be vibrating in segments. String will start vibrating in segments like this. Suppose that's the fixed end. Okay, let me rub this portion. Let me draw it again. Yeah, so the standing wave will be formed in a string in few segments. This is just a snapshot of standing wave. If you look at the video, this segment will start coming down, this segment will go up, and this segment will start coming down, and so on. So the motion of these segments will be just up and down. In traveling wave, as you know, that if a wave is produced in a string, these crests and troughs, they travel in some specific direction. So these crest and these trough, they are traveling in some direction. But standing wave is a bit different from these traveling wave, because the crests and troughs, they are not traveling, rather they are just bumping up and down. They just move up and down. So crests are becoming trough and trough are becoming crest, moving up and down. The reason why these crest and trough are just moving up and down is can be explained this way. See, in a string, these two waves, when they were traveling, and suppose there is another wave which is traveling in other direction, at different points, when crest meets crest, at different points, they are going to increase the amplitude of the string. And at different point, when trough meets trough, again they are going to increase the displacement of each point and become bigger trough. But those positions in a string where crest of the individual waves are meeting the trough of the reflected waves, so these are two individual waves moving in opposite to each other, so those locations where crests are superposing with trough, those points will never move. For example, if you go back to this picture, this point, okay, this point, this one, these are the points which will be having zero displacement. And the reason why these points have zero displacement is because at these points all the time, trough of one wave is superposing with crest of other wave. So they cancel each other, because trough wants to move the particle down and crest wants to move the particle up. So they cancel each other and that point will not move at all. But what about these locations? These are those special locations where trough and where two troughs or two crests are meeting. For example, if you look at this position, a traveling wave from one end is asking the particle to go up by some few centimeters, and the reflected wave coming from other end is also asking the particle to go up by a few centimeters, and as a result that particular particle will move maximally high from the equilibrium position. And same will occur in this region. So you can understand what is happening at this region. Trough of one individual traveling wave is asking the particle to move down, and trough of other individual wave is also asking the particle to move down. So at the same time, these two troughs are overlapping at this point. So as a result, a particle will move down maximally away from equilibrium position. So all region of the string is moving except these points. These are the only points not moving at all. because of destructive superposition of individual waves. Now I'm going to make a picture of standing wave once again. Consider this to be a fixed point, and the string is just moving up and down in this fashion. If it moves quickly, so what you will observe is string present here, represented by the dash line, and like these are not two strings, this is just one string, but at different times. So you can see there are loops formed. This is one loop, second loop, third loop, fourth loop, and so on. Number of loops depends on the frequency of incoming waves. Now these are the points which will not move at all. So these are some special points. So let us give special name to these points. Special name for these points are nodes, N. And these positions where the particle is moving up and down with maximum displacement, so these points are called antinodes. So nodes are those locations where particles have zero displacement, and antinode are those positions where particles are moving with maximum amplitude. Energy in these waves do not travel. In traveling wave, energy do travel, like for example if the progressive wave traveling in this direction and the one which is reflected from other side, energy do travel. But in standing wave, energy is stored at these locations, at antinodes. So all of the energy is stored at antinodes. This wave can be formed on water surface, like for example if someone disturb water surface from one end and water wave travel and then reflected back from reflecting surface. So you can see water bumping up and down, and you will not observe crest traveling, rather crest and trough will locally just move up and down. Okay, so this is how standing waves are formed. So I'm just going to summarize what I said about the formation of standing waves. Two identical waves. Identical, by saying identical I mean having same velocity, having same frequency, having same amplitude, and if these waves are continuously traveling in opposite direction, when they overlap with each other, they're going to form this pattern, and we call this pattern by name standing wave or stationary because it looks like these waves are not moving. Okay, now let us do some quantitative discussion. For example, if you have a string and the string is fixed at one end, and there is a vibrator or something which will vibrate this end to produce waves, and waves will travel and will come back. So after superposition you will see standing wave. The question is with what frequency this end should be vibrated to form a standing wave. So keep in mind, students, that all frequencies are not allowed. There are few specific values of frequency with which the string should be vibrated in order to see this kind of pattern. If you start vibrating the string with any value of the frequency you like, you may not observe this kind of loops in the string because some specific values of frequencies allowed. So these are discrete values of frequencies with which if you vibrate the string, then you can see standing wave forms in the string. So I can say these values, these frequencies are quantized They are discrete level of frequencies. Depending on length of the string and depending on tension in the string, but that's beyond the scope of the syllabus, so I'll not discuss the tension and the relation of length with the frequency. So now students, there are few modes of vibration. The minimum mode of vibration will look like this. So this is the lowest frequency possible for the standing wave. So string just move up and down. Okay, it just move up and down with having only one antinode and two nodes at the ends. This is a node point because the string is fixed, and I can assume this to be a node because the string is vibrating here with very low amplitude. But in the middle you will see the string vibrates with maximum amplitude. Now students, if you remember, looking at the wave one wave structure, the distance from here till here is wavelength, lambda. Now if this is a standing wave, then you can see string vibrating up and down in two loops with this and node, here antinode and node again, and so on. So here I can say that the distance between node and consecutive antinode, I'm talking about this distance, that's equal to lambda over 4, because the whole lambda is divided into 4 segments. So these are 4 segments, so lambda is divided into 4 parts. So keep in mind students that the distance between node and antinode is lambda over 4. So I'm going to use this value in deriving an equation for the frequency or minimum frequency of the standing wave. Minimum frequency of the standing wave is also called as fundamental frequency. Fundamental frequency, because that's the minimum value. Now consider length of the string starting from here till there is L. That's the length of the string. So the relation between length of string and wavelength is L equals to 2 times lambda over 4. Why 2 times lambda over 4? Because you can see from node till antinode, this part is lambda over 4, and from antinode till this node, it's again lambda over 4. So it's basically 2 times lambda over 4. Now making lambda as a subject, so you can write equation as 4L over 2, or this implies that lambda equals to 2L over 1 by cancelling 4 and 2. Since this is the fundamental mode of vibration of a standing wave, I can also call it as first mode of vibration, so better to write 1 as a subscript with lambda. So I'm going to make a box because this is an important equation. Now we know that frequency is related with the velocity of the wave by this equation, v over lambda. Now if I put 1 here, because that's a fundamental frequency, and 1 here obviously, but I'm not going to put 1 with velocity, because velocity of a standing wave do not change with changing the mode of vibration. It only depends on the length of the string and tension of the string, but I'm not changing length and tension at all. So frequency F1, which is the fundamental frequency, equals to V and from there, if you substitute the value of lambda, you can get 1 time V over 2L. So that's the equation for fundamental frequency. So for example, if you put the values for the velocity, whatever the velocity is, if you put the value of length of the string, for example, I just assume here the answer is 4 Hertz. So what this number 4 Hertz means, it means that every point on a standing wave, every point except nodes, because nodes are not moving at all, every point on the string are vibrating up and down 4 times a second. Like for example, it starts from here, 1, 2, 3, 4, 1 second completed. So in every second, every point will vibrate 4 times in a second. So all points have same frequency but having different amplitudes. Points have different amplitude. You can see this point vibrate with a smaller amplitude, this point vibrate with a maximum amplitude, and this particular point vibrate with a very small amplitude, and node obviously have no amplitude, 0 displacement. So that's the meaning of 4 Hertz. So I can say this is a fundamental frequency. So this particular string having the individual waves moving in 2 different directions with some specific velocity will make a standing wave of this frequency. Now what about the second mode of vibration? So once again, I'm going to draw a standing wave with second mode of vibration. The picture for the second mode of vibration will look like this. So having nodes at these 2 ends. Now here we can have 2 antinodes, one here and one here. So if the string vibrates very quickly, then you can see such loops. So this is how loops will look like in the standing waves. So it has 2 antinodes and 3 nodes. This is also a point of node, point where it's not moving. So the length of the string is the same. Length of the string is not changed, plus the tension in the string is also the same, so obviously the speed will remain the same. Now if you look at this picture, length equals to 4 times lambda over 4. Why 4 times? Because the distance from node to antinode, this is lambda by 4, from antinode to node again lambda by 4, from node to antinode again lambda by 4, and from antinode to node again lambda by 4. So these are 4 parts of lambda by 4. Or if you want to write lambda as a subject, so lambda equals to 4L over 4. Okay, I can write this equation as 2L over 2, although I made no difference because 4 over 4 and 2 over 2 is same thing, but there is a reason writing this lambda in this form, and that I will tell you in a couple of minutes. So since this is second mode of vibration, so it's better to write 2 here, because that's the second mode. Now frequency of this standing wave, this one, is again can be written as V over lambda. Since this is second mode of vibration, so better to write 2 here and 2 here, but not with V, because the velocity of these waves is same, because I haven't changed the length, I haven't changed the tension in the string, so velocity have to be same. That's the reason I'm not writing 2 with velocity. Now if you put the values for V sorry, for the lambda. So it would be 2L, 2 here. Okay, so I can write this equation as F2 equals to 2V over 2L. So this is the frequency for the second mode. Now if you put the same values of velocity and length, same as these values, for example, the values which I put it here, and I assumed the answer was 4. So if you put the same value in this equation, you will see you will get a number which would be double of 4. Why double of 4? Because here V over 2L is 4. So it means frequency doubles, which becomes 8 Hertz. That means that every particle on the string now will vibrate quickly, will vibrate 8 times a second. So string is going to vibrate quickly, but the amplitude will be smaller than the amplitude of this standing wave, and the wavelength obviously also becomes smaller. So here this is the equation for the second mode of vibration. Now let us discuss the third mode of vibration. Once again, the same string, same tension, same length. So the third mode of vibration will look like this, with 3 loops, starting from node, and both of these ends are node. So if the string is vibrating quickly, then you will see such kind of loops with antinode here, antinode here, antinode here, node here, and node here. So length of the string is not changed, so that's L. Length of the string is L. Now if you look at the picture closely, what you will find is L equals to how much time lambda by 4? 1, 2, 3, 4, 5, and 6. So these are 6 parts, 6 times lambda over 4. So if you want to simplify it, you can cancel these numbers like this, or you can write this equation in terms of lambda, making lambda as a subject. So wavelength equals to 2L over 3. I'll put 3 here in the subscript because this is the third mode of vibration. Now what about the frequency for the third mode of vibration? That's equal to V over lambda 3 with same reasons. This implies that F3 equals to 3 times V over 2L. So now I hope you got the point why I was writing this wavelength by replacing 4 by 2. Because if you look at the sequence of the frequency for the first mode of vibration is 1V over 2L. Frequency for the second mode of vibration is 2V by 2L, and frequency for the third mode of vibration is 3V over 2L. Now if you put the values, same values as put it in the first mode of vibration, the answer would be 3. 3 comes from here, and the answer for V over 2L, which was the fundamental frequency 4, it becomes 12 Hertz. So this string now will vibrate with 12 Hertz, means every particle is going to vibrate 12 times a second. So students, what I'm trying to explain is the string having specific length and having a specific value of the speed of the individual wave. This string can have a standing wave with the frequency 4 or with the frequency 8 or with the frequency 12. So only these values of the frequencies are allowed. Other than these values, like all any values in between 4 and 8 or 8 and 12 are not allowed. So values of the frequencies are discrete. There are a specific set of values for the frequency for which you can see standing waves in the string. Obviously, if you change the length of the string, or if you change the tension in the string, which will obviously change the velocity, these values will change, but again you will find a new set of discrete values for the frequency. So the final conclusion about frequency is that frequency can have some discrete set of values for which you can form a standing wave in a string. If I combine all those three equations, I can write a general form for the frequency as n times v over 2L. So this is the general form of the frequency for standing wave for any mode of vibration. So it's better to write n in the subscript, where n starts from 1, 2, 3, 4 and so on. 1 means, if you put 1 in this equation, it means you are calculating fundamental frequency, and if you put 2 in this equation, you are calculating the frequency for the second mode of vibration. If you put 3 in this equation, it means you are calculating the frequency of particles in a standing wave for third mode of vibration, and so on. Okay, now students, we are going to use this equation in some problems. In a few problems, I have few problems here. Before discussing a quantitative problem, you can go through this conceptual question. Here the question says that the diagram below shows a standing wave on a string. A standing wave is created when two progressive waves traveling in opposite direction combine. State the phase difference. That is the phase difference is the phase of those two traveling waves. Are they in phase or are they out of phase between x and between the progressive wave at x and y? So students, here there are 2 points given in the standing wave, point x and point y. So they are asking, in the question they're asking that when these two progressive waves and they travel opposite to each other from different direction, opposite to each other, and when both of these waves meet, so how they are meeting at point x and how they are meeting at point y. So at point x, they are meeting out of phase, and the reason is because here is a node, and node can be created if crest of one wave meets with the trough of another wave, which is out of phase meeting. And point y, at point y, these two waves are meeting in phase because you can see antinode is created, and antinode means the particle is displacing maximum high, and maximum low means crest and crest, or trough and trough are meeting. Here's another question. In this question, a stationary wave is established in a string which is 120 centimeter long and fixed at both ends. You can see node here and node here. So particles in the string is vibrating with 120 Hertz. The question is to determine the wavelength and the fundamental frequency for the string. Like the particles are now, at this moment, particles are vibrating with 120, but what could be the minimum frequency for particles in the string, in this specific string? And we are also going to calculate the wavelength. Now, if you closely look at the picture of the standing wave, you will find that there are 1, 2, 3, 4 antinodes. So 4 antinode means this is the fourth mode of vibration. So I can say n equals to 4. Okay. Now if I move down to this equation, if I go down to fundamental equation for the frequency, or we know that the frequency Fn equals to n V over 2L, but if I shift V downstairs here, so n over 2L, and flip the equation, so it becomes V over Fn equals to n over 2L. So left hand side is nothing but a wavelength, so wavelength equals to n over 2L. So this is also equation for the a general equation for the wavelength, but the proof of this equation is not important. If you want to note down this equation with you, it's useful for solving problem in a quicker way. So look at this equation, and we'll go back to that problem. Here. Now students, the equation was n lambda n equals to n over 2L. Okay, so this is the fourth mode of vibration, so better to write 4 here, and n is 4. 2 into 120 cm, which is 1.2 meter. You have to change centimeters into meter, and if you solve this in one shot, the answer would be 0.6 meter. So that's the wavelength of fourth mode of vibration of the standing wave. Now what about the fundamental frequency? To calculate the frequency, we know from the general equation of the frequency n times V over 2L, or it's not important to use velocity because velocity is not given. We know that Fn equals to let us write here, Fn equals to n V over 2L, but this value is the fundamental frequency. Fn equals to n, so V over 2L is nothing but a fundamental frequency. If you remember, F1 was equal to 1V or just V over 2L. So I have replaced a fundamental frequency in this equation. So the frequency for the fourth mode of vibration was how much? You have to, it was 120 Hertz. So if I put here 120 equal to 4 multiply F1. So if you solve for F1, the final answer would be 30 Hertz. So this is the minimum frequency with which particles in this standing wave can vibrate. If you want, you can use this equation in other ways, but there are a variety of ways using equation. Okay, now coming to second question. Here they said a string of 75 cm long is vibrating with 15 Hertz. Calculate speed of progressive waves with which have interfered to produce a stationary wave. Now here in this picture we need to calculate the speed. Speed of who? Speed of individual waves which were traveling in opposite direction and they meet. So we need to calculate that speed. Now equation for the general equation for the frequency is nV over 2L. Now look at the picture and pause the video and just ask yourself which mode of vibration this is. So if you count the number of antinodes here, 1, 2 and 3, so there are 3 antinodes. So 3 antinode means the string is vibrating in third mode of vibration. So I'll just write here F3 equals to 3v, because n is 3 here, into 2l. Now the physical quantity which I'm going to calculate is velocity, so make velocity as a subject. So equation becomes as 2l f3 over 3. Now if you put the values, 2 multiply length, which is 0.75, changing centimeters into meter, multiply the frequency, which is 15. So that's the frequency of the third mode of vibration, divided by 3. So if you solve this equation, the final value for velocity would be 7.5. So velocity here is 7.5 meters per second. That's all, students. Thank you.